Our first question is to do an estimate of the amount of force required to stretch a spring 2.3 meters with a spring constant of 54 newtons per meter. So we start with our formula. Force of the spring is K delta X. We're looking for the force. The spring constant is, we'll put that to a nice number. We'll make that 50. And the delta X, 2.3, is about 2. So we'll say it's about 100 newtons. So about 100 newtons. That's how much force. And the next problem, we have two friends working on cars with their mothers, doing some work on the suspensions and the springs. And the first question is we want to know the spring constant of the springs in the upper Saddle River friend's Mercedes. So we could picture a car like so. And there's the rear wheel. The person gets inside like so. Well, the car then sinks. We are told it sinks 5.6 centimeters. So it compresses 5.6 centimeters. And what we know at that instant in time then, after the car compresses, is that the forces are balanced. The force of gravity is equal to and opposite to the force of the spring. So if we want to know the spring constant, we start with our Hooke's law. Force of the spring is K delta X. We want the spring constant by itself, so to get rid of the delta X, we would divide both sides by delta X. Delta X divided by delta X is 1, so we're left with the spring constant is the force of the spring over delta X. And what we just said was the force of the spring is equal to the force of gravity over delta X. Well, the force of gravity is mass times the gravitational field strength. So for the person in Upper Saddle River, they are 78 kilograms. 9.80665 gravitational field strength, and the deviation, the displacement is 5.6 centimeters. We do the math on that. We get 136.59. But upon closer inspection, we should realize that it's the rear end, and the rear end has two wheels, and the rear end has two springs. So that compression that's being executed is against two springs. So if it were one spring, it'd have a strength of 136, but if it's two springs, it would only be half that. So the half of that is 68.296. And we're looking for the spring constant, so that is in newtons per meter. We look at our significant digits now. This has 2, this has 6, this has 2. So our final answer would have two significant digits. So the final answer then is K equals 68 newtons per meter. Now we're asked to do the same thing for the Hooke's friend. So we have the spring constant is the force of gravity over delta X, which is mg over delta X. And we realize we also have to divide that by 2. So we have 94 times 9.80665. And the delta X for this one is 8.4. And in doing that, we end up with 54.87 newtons per meter. And again, we have two digits in this one, two digits in this one. And that gives us a final answer of two digits. So our spring constant K is 55 newtons per meter. Now, lastly, we are asked if the Hooke's friend is correct. The Mercedes springs are stronger. Well, the Mercedes springs are 68 and the Ford F-250 are 55. So yes, the Hooke's friend is correct that the Mercedes springs are stronger. Since the spring constant of the Mercedes is greater, 68 newtons per centimeter, than the spring constant of the Ford F-250, 55 newtons per centimeter, the springs are stronger in the Mercedes.